Okay, so this is sort of a follow-up to the other video I did on method of standard additions. And that one was for my students. I made that one a couple of years ago relative to the time period that I'm in right now. And it occurred to me, looking back at it, that I could probably use an example rather than just kind of going over how to do it. So this is that example. It's in, I don't remember if I mentioned it in the original one, but in class what we do is we have the students try to figure out the amount of calcium in orange juice. I believe it's orange juice. It's been other juice drinks in the past, but in any case, we have calcium in some kind of drink here in this case that we'll look at for our example. And so we want to consider, and I have some data that I made up, so don't take these values to be like anything like serious here. They're just kind of numbers that I made up. So we have our sample here, so kind of pretend this is our drink. This is the container that holds our beverage. And that has some unknown concentration. We don't know what it is. That's what we're trying to find out. Then we've made a standard solution. Maybe we made it by taking some calcium. We made it somehow. Okay, somehow or other, we made this solution, and that's just going to be a mixture of, I suppose I shouldn't say mixture, but solution of water plus calcium. Okay, that's all that is. Maybe I can zoom in a bit. Let's see, slide this over. Professional outfit here. There we go. Get it figured out eventually how to do this well. There we go. Okay. And then what we're going to do is we're going to make a series of, we're going to do 6 solutions. So I think I highlighted that you could do 5, but I'm pretty sure I also mentioned that anything between 4 and up. The more you do, the better. But of course, there's a limit to how much time you have if you're making solutions. And there's a limit to how much beneficial that next solution is. So for instance, if you only do 2 solutions, adding in a third one is way better than 2. 4 is a lot better than 3. 5 is better than 4. 6 is better than 5. And 7 is, you know, it's better. Like each one is better. You get the idea. So we have to decide how much of our sample we want to put in each one. And remember, we put the exact same amount in each one of them. And so here we're going to do 5 milliliters. So it's going to be 5 milliliters for every single one of these, of our sample solution. So that's going to be 5, 5, 5, 5, and 5. For the standard solution, this is where it changes. So remember that with the first solution, we're going to want to put 0 milliliters in that one. That first solution, I have to make sure that it has 0 in there. It can be a little bit weird to think about it that way. Normally when we're making solutions, we don't think about things in terms of no volume in one of them, but when you're doing this method, you have to make sure that there's no standard solution in at least one of your measured solutions. There's still going to be the solute in there. The solute for us here is calcium. That's still going to be in there, and it's in there because you've added some of the sample. So that one's going to be 0. I just want to look over here at the values that I want to use. So I did work through this before. I have 1 milliliter there, then I did 2, 4, 8, and 10. All milliliters, and the total volume of our solutions here is going to be 50. So remember, I'm not adding up these two. I'm not adding volume of sample to volume of standard. That would be only 5. I'm going to be adding 45 milliliters of solvent to get to this total volume. And every single one of these is going to have however much solvent added to it to get you a total volume of 50. And so if your lab has volumetric flasks, which are going to be the ones that are kind of shaped like, I'll draw them up here. Those are going to be the ones that are kind of shaped like this, with like a long neck. on the top, kind of like that. And there's probably a little line up there that you would fill it up to. You would want to use a 50 milliliter volumetric flask to make these. Those are good for making solutions in lab. That way you can make sure that you get this final volume of 50 milliliters. Okay. So while you can do just one method of graphing it, you don't have to do all of them. I'm going to show you myself, I guess, doing 3 of them. That way you can see that it doesn't matter which way you do it. So we'll just remind ourselves of what those ways are, and we're going to call this like method 1. Put a line here to divide this out. So we're going to call this like method 1, and we're going to say this is going to be absorbance, and we're going to graph this against concentration of the standard solution, which I should mention, concentration of our standard solution is 2 moles per liter. Starting to see that maybe I wrote a little bit too small. Hopefully you can kind of make that out. 2 moles per liter. So we're going to graph it versus, I have a lot of items on my desk here sort of blocking my way. Absorbance versus concentration of standard times volume of the standard solution added. Remember that that's the only thing that changes in this array of solutions is the volume of standard that we added. The concentration of the standard is the same, that's 2. The volume of sample, the unknown solution, added, that's the same, that's 5. And the final volume is the same. So the only thing that's changed that we can control, that we know, is the volume of the standard solution. So we have to make sure that that's in there. Divided by total volume, and then method 2 is going to be absorbance versus concentration of standard times the volume of standard. And then method 3, which you cannot see, method 3 is going to be absorbance. Should have drawn that up a little bit higher maybe, versus volume of standard only. So when we do that then, from method 1, we're going to have, from method 1, we'll write them here so that they can see them a little bit better. From method 1, we're going to have that the concentration of the sample solution is going to be equal to minus the total volume. Well, we'll write the x-intercept first. Minus x-intercept times total volume of the measured solutions divided by the volume of sample solution added. Method 2, it's going to be equal to minus the x-intercept divided by the volume of sample solution, which remember is the same for all solutions, so we don't have to worry about that. And then for method 3, it's minus x-intercept times concentration of standard divided by the volume of the sample solution. So these are the 3 ways that we're going to be calculating it then. And they're each going to correspond to one of these 3 types of graphs. Now I'm going to be switching over to Excel soon, and that's where I'm going to be doing it. But you don't have to do it in Excel. You can do it on one of these if you like. You got to be able to get the intercept and the slope. If you're really pressed for not being able to use a calculator to find the intercept and slope, you don't need to worry too much. You should maybe start sweating a little bit, but it's possible to calculate the slope and intercept from all of these values without a calculator. It's just going to take you much, much longer. So the data that we'll be using is this here. Can it all fit? Nearly. There we go. There. This is the data. We have the solution number, 1, 2, 3, 4, 5, and 6. The volume of standard solution added, So there's that, and the absorbance that was measured. And again, kind of made these up, so don't take these to be some kind of, actual measurements. But I did make them up to be at least marginally believable. Also, these absorbance values are a bit randomized, so we're not going to get perfectly straight lines here. Okay, so this is the data. You can go ahead and enter it into whatever way your favorite way to do it is, and then you can follow along. We're just going to be working out how to do this. Let me switch over to Excel here. Let me grab my slightly quieter keyboard before I do that. Display. There we go. Okay, now that we're on my slightly quieter keyboard, we can do this a little bit more slightly quietly as I move all of my items around. All right, got to clear off this desk. Okay, so what we've typed in here, or I should say what I've typed in here, is we have the total volume of these solutions. That's up here. I can try to zoom in some. There we go. Total volume of the solutions here. Now we've put that in milliliters, and that was 50. The volume of the solution, this volume of the sample was 5 milliliters, and the concentration of the standard solution in moles per liter was 2. Now you notice that the concentration is in moles per liter, whereas the two volumes is in milliliters, and so you might think, well, we'd better change those units, right? We can change this one into 0.005 and change this one into 0.05, but it doesn't really matter. It certainly doesn't hurt to do it, and if you're nervous about it causing issues, then by all means, change them. But it doesn't actually end up mattering. In particular, we can see that it doesn't matter. I can just kind of quickly show you why it doesn't matter here. Go to this, zoom out of it, is we can see that when we calculate the concentration of the sample, we see a ratio of these two volumes. And so if these two volumes here have the same units, we're going to end up with those units canceling out. And then we'll just be left with whatever units the x-intercept has. The x-intercept, as we'd seen, is, well, we can write that down. Oops, sorry about that sound. I dropped my keyboard. The x-intercept for all three of these methods, it doesn't matter which method you're doing, the x-intercept will be equal to negative the y-intercept value divided by the slope value given to you by the data analysis. The y-intercept will have no units because absorbance has no units, and the slope will have units of absorbance over whatever this is, which means the slope has units of 1 over whatever this is. Okay? And so what we see then is that we will end up with those units working out for us. Okay? And it can also be a good exercise in any case to kind of go over that for yourself and prove to yourself that that works. In a situation like an exam or something, or when it's really important, I'd just go ahead and switch those just to be safe. But let experience tell you when you can do that, and I'm telling you that it's fine here. So what we have here then is our little table that we just kind of wrote up that was written out on the page before. So the first thing I'm going to do, get my keyboard working. Okay, first thing I'm going to do is say that we have, let's see, where do I want to put the graphs? I have no idea how far I can zoom out to where you'll still be able to read this. Maybe I can minimize this. I have to access that in a bit. Maybe I can put it here and we can say method 1. So method 1 was going to be a graph of, we'll say method 1, we'll do x values. Yeah, let's do, should have thought about how I wanted to do this before. So this is going to be our x values stuff, and this is going to be method 1. This is going to be method 2. It's going to be method 3. So this will be, so this is the x values. Method 1 was concentration of the standard. It's going to be this guy, times the volume of standard solution added, so times those, divided by the total volume of the solutions. So there's that. Method 2 was concentration of the standard, that, times volume of the standard, which you notice is just the moles of stuff from the moles of solute from the standard that's now inside of that entire sample, entire solution. I should try to reserve the word sample to refer to the unknown solution. Method 3 then is just these guys here, volume of the standard solution. So we'll go ahead and we'll take a look at a graph. Now all of these graphs, we might just plot, we might plot all three. The graphs are all going to look essentially the same. So we'll call this one method 1. The x values, those there. The y values, those there. So there's that. Make it a little bit smaller there. Go up here. Just going to make these really quickly. Not trying to do a tutorial on how to use Excel right now. This is just making a graph of the method 2. I'm going to have to rely on you looking back at any notes you might be taking on what I'm saying to see what those equations are for the x values. 3. Those. And absorbance. Okay. Oh, come. There we go. And there. Same size. A little bit bigger. Same size. A little bit smaller this way. Okay. So what we see then is the shape of these graphs is the same, right? It goes up a bit from the first point to the second one, then a little bit flatter, right? There's a big gap here between these ones, and so the shape of them is exactly the same. The y values are all exactly the same because they all have exactly the same absorbance. The x values, though, are different, as we can see then. So there's really just some kind of scaling happening on the x-axis, which shouldn't really be too surprising, since if we look at what we did for our graph, we have volume of standard solution there in all three of those. And the only thing that's different is this is just volume of standard solution, but these ones have been multiplied by concentration of standard. These ones have been multiplied by the ratio of concentration of standard to total volume of the solution. So there really is just some scaling going on there. So that shouldn't be too surprising. I'm going to call this the x values, and down here we're going to do the y-intercept, and this will be the slope. I'm having to move my head all around to try to see the thing. I have my document camera in the way. So this is going to be the y-intercept. So in Excel there's a nice little function for that called intercept. We need to give it the y values and the x values. So there's that. And the slope can be found by doing this, y values, x values. There we go. So if we come up here and I make these ones, there we go. Oops, this one too. There we go. And now I should be able to do that. There we go, good. Do the same thing here, highlight it. F4, there we go. There. So don't pay too much attention to the specifics of what I was doing there if you're not interested in learning Excel. all we're doing here is just calculating the y-intercepts for the three methods here, method 1, 2, and 3, and the slopes for those methods. And remember, although the graphs look the same, they do have different slopes because the x values are different. They're just scaled visually right now in such a way that they look exactly the same. So that's why they have different slopes. The intercepts should all be the same because they all have the same y values. Then the x-intercept, like we said, is negative y-intercept divided by slope. There we go. So those are the x-intercepts for each one of these methods. Then now we're going to use, and I'll show it here just to kind of try to remind ourselves. Okay. For each one of these methods, then we have a different equation for the concentration of the sample solution. So we have to make sure that we use the correct equation for whichever method we are currently looking at. It's very, very easy to accidentally use the wrong one, so we just have to be careful about which one we're doing. This is going to be the CS. And like I said, the units work out that this will be moles per liter. For method 1, we're going to have minus x-intercept times total volume, which I had that up here, that was 50. So we'll just type in 50, and divided by the volume of the sample solution, 5. Okay. This one was, method 2 was negative x-intercept, this guy, divided by volume of the sample solution, which was 5. Oh, same number. How about that? We can maybe get these a little bit nicer looking. There, a little bit easier to look at here maybe, huh? Let's do that. So these are the calculations then. I suppose these are calculations as well, but let me move these down. There. Okay. Method 3 was negative x-intercept times concentration of the standard solution, which was 2, divided by the volume of the sample solution, which was 5. Volume of sample solution, 5. There we go, 1.46. And so what we see then is the concentration of the sample solution. The concentration of our unknown solution is about 1.46 moles per liter. Now, of course, there's some error associated with this value. Like I said, the absorbance isn't a perfectly straight line, and that's a good indicator that there is some error there, and there's some error in any measurement. And I did randomly generate these absorbance values, so there's definitely some error associated with this measurement. You know, the error analysis on this is something that we can do at another time, but we just want to make sure that we don't conclude that it is definitely exactly 1.46, but that it is about 1.46, probably reasonably close to 1.46. So we could go ahead and use that value then. So that's the concentration in the sample solution. That's how you would do the data analysis for method of standard additions.